morning. This is module 4 of stochastic process video course, and in this we are going to discuss the limiting distribution and the stationary distributions in the lecture 4. In the last 3 lectures we have discussed the time homogeneous discrete time Markov chain, and in the last lecture, that is on lecture 3, we have discussed classification of states, concepts and the definitions. But we have not discussed the simple examples for that. So, in this lecture I am planning to explain, I am planning to give a few examples for the classification of states. Then I am going to give the definition of limiting distributions, then followed by stationary distributions. Then the same examples I am going to explain how to get the stationary distribution if it exists. So, if you recall our earlier lecture, that is a lecture 3, we have given the lot of concepts. Through those concepts we can classify the states, the state as a transient state or recurrent state. Then the recurrent state can be classified into the positive recurrent state and the null recurrent state, and you can find out the periodicity of the states, and if the period is going to be 1, then we say that state is going to be the aperiodic state. And if any state is going to be a positive recurrent and aperiodic, then we say that state is the ergodic state. And if a one step transition probability, if Pii is equal to 1, then that state is going to be called it as a absorbing state. And also we have discussed irreducible Markov chain, that means the whole state space is not able to partition into more than one close communicating classes, then that is going to be closed. That is going to be called it as a irreducible Markov chain, otherwise it is a reducible Markov chain. Now I am going to give simple examples, through that we are going to explain the classification of the states. The first example, the simplest one, in this first simple example we have only 2 states. So, the state space contains only 2 elements, 0 and 1. The transition, the one step transition probability from the system is moving from state 0 to 1, that probability is 1, and the system is moving from the state 1 to 0, that probability is also 1. So, the one step transition probability matrix can be obtained from the state transition diagram, both are one and the same. So, this is the one step transition probability matrix and this is the state transition diagram, both are one and the same. So, 0 to 0, that probability is 0, 0 to 1, that probability is 1, 1 to 0, 1 to 0, that probability is 1, and 1 to 1 is 0. Now, we can find out whether these states are going to be a recurrent state or transient state. If you recall, to find out the recurrent state or transient state, you have to find out what is the Fii. So, we start with the state 0. So, if you try to find out F00 of 1, what is the probability that if the system start from the state 0 and reaching the state 0 in exactly first step for the first time, then that probability is not possible, that is equal to 0. If you try to find out F00 of 2, first visit to the state 0, given that started in the state 0, exactly in the second step it reaches the state 0, that is possible because by seeing the state transition diagram, you can make out the first step the system is moving from state 0 to 1, and 1 to 0 it is possible coming back to the same state taking exactly 2 steps for the first time. Therefore, F00 of 2, that probability is 1. And by seeing the state transition diagram, you can visualize, since it comes to the same state exactly second step, therefore, all the further steps for the first time, that is not possible. Therefore, all the f 0 0 of n, that is going to be 0 for n is greater than or equal to 3. For n is greater than or equal to 3, the f 0 0 of n is equal to 0. Now, if you try to find out what is capital F 0 0, that is the probability of ever visiting to the state 0 starting from the state 0, that is going to be the summation of f 0 0 superscript within bracket n for all n vary from 1 to infinity. If you sum it up, then that is going to be 1. Since f 0 0 is equal to 1, you can conclude the state 0 is the recurrent state. You can conclude this state 0 is the recurrent state. Similarly, if you do the same exercise for the state 1 by starting with f 11 of step 1, what is the probability, f 11 of step 2, what is the probability, and f 11 of all the n's, and find out the summation. So, you will end up f 11 is also going to be 1. You can conclude similarly the state 1, that is also recurrent state. Here, after finding the recurrent state, now we can find out whether this is going to be a positive recurrent state or null recurrent state. For that, you have to find out what is the mean recurrence time or mean passage time. So, try to find out what is mu 0 0, that is nothing but summation n f I of n. N varies from 1 to infinity. So, here the I is nothing but 0 0 n times f 0 0 of n, because this takes the value 1 for f 0 0 of 2, therefore, you will get 2 times 1 and all other quantities are 0, therefore, this is going to be 2. And this is going to be a finite quantity, therefore, you can conclude the 0 is the state 0 is the positive recurrent state. The same exercise you can do it for mu 11, that is also you may land up getting the value is equal to 2, therefore, you can come to the conclusion the state 1, that is also positive recurrent state. So, in this finite discrete time Markov chain, you have 2 states and both the states are going to be a positive recurrent state, and both are the communicating states. Therefore, you have a class that has the 2 states and the state space is also 0 and 1, and the close communicating class is also 0 and 1. Therefore, you are not able to partition the state space into more than one communicating class and so on. Therefore, we land up this Markov chain is going to be, this Markov chain is the irreducible Markov chain. This Markov chain is a irreducible Markov chain because the state space has only 2 elements and both the states are communicating each other, and we land up only one closed communicating class. Therefore, this is going to be a irreducible Markov chain. We can find out what is the periodicity of these states also. You can find out the periodicity for the state 0 by evaluating D0, that is nothing but what is the greatest common divisor of all possible steps in which the system is coming back to the same state. So, if you find out the system can come to the same state, if you see the state transition diagram, if the system starts from the state 0 coming back to the same state either by 2 steps or 4 steps or 6 steps and so on. you should remember that when you are finding the periodicity, you are finding the number of steps coming back to the same state, not necessarily the first visit. Whereas the F00 of n, to conclude it is a recurrent state, you are using the first time reaching that state in the exactly nth steps. So, there is a difference. So, the GCD of all the possible steps in which the system is coming back to the same state. So, it can come back to the same state 0 in 2 steps or 4 steps or 6 steps and so on. So, the GCD is going to be 2. That means the period for the state 2, sorry, the state 1, the state 0, period for the state 0 is 2. Similarly, you can find out what is the period for the state 1 also. If you do the same exercise, but seeing this diagram you can make out the state 1 also going to have the GCD of 2, 6, 2, 4, 6, 8 and so on. Therefore, the period for the state 1 also going to be 2. Otherwise also you can conclude both are communicating states, since the period for the state 0 is 2 and since the state 1 is communicating with the state 0, that means it is accessible in both ways. Therefore, the state 1 is also having the same state, same period. In conclusion, you can make out if you have a one class with more than one states, then all the states are going to have the same period. Therefore, the state 1 is also have the period for the state 1, that is also 2. That means, this example you have only 2 states and this is a irreducible Markov chain and both the states are positive recurrent with the period 2. So, that is the way using the classification of the states we come to the conclusion of this particular example. Later we are going to find out the limiting distribution and the stationary distribution and so on, but for that we need the classification. Here also you can visualize where the system will be for a longer run if the system start from the state 0 or 1. You can visualize because it is only 2 state. By seeing the state transition diagram, you can make out, suppose the system start initially the state 0, at every even number of steps it will be come back to the state 0. In a longer run, based on the number is going to be even or odd, accordingly the system will be in any one of these states. Similarly, in a longer run, you can make out if the system start from the state 1 initially, all the even number of steps it will be come back to the same state 1 and all the odd number of steps it will be in the state 0. In the longer run also it is going to be happen in the same way for a even n and the odd n, accordingly the system will be in any one of these states. In a longer run also the system will be any one of these 2 states only, because it is a irreducible Markov chain, because these 2 states are communicating each other. Therefore, in a longer run the probability that the system will be in any one of these states will be a some value and only the system will be in any one of these 2 states only. Later I am going to give the definition of the limiting distribution, through that I am going to explain the same example again. Now, we are moving into the next example. Example 2. Here I am going to discuss a reducible Markov chain. Here also we have only 2 states. The probability of system is moving from state 0 to 0 in the next step, it is the probability is 1, and the system is coming from the state 1 to 0 in one step, that probability is 1. So, this is a state transition diagram of a time homogeneous discrete time Markov chain. So, I am going to write what is the one step transition probability matrix for this state transition diagram or for this discrete time Markov chain. So, 0 to 0 one step, that probability is 1, 0 to 1 is 0, 1 to 0 is 1 to 0 is 1, 1 to 1 is 0. You can verify whether this is going to be a stochastic matrix, because each elements are lies between 0 to 1 and the row sum is 1, therefore, this is a stochastic matrix. So, both are equivalent, the state transition diagram and the one step transition probability matrix is one and the same. Now, we will try to find out what is the classification of the states. Go for the state 0, the P 0 0 of 1, that is 1, that is one step transition of system is moving from the state 0 to 0, that is going to be 1. This implies the state 0 is a absorbing state. Now, we will try to find out what is the classification of the state 1. So, if you find out f 1 1 of 1, what is the probability that the system will come to the state 1, given that it was in the state 1 and the first time visit to the state 1 exactly in the first step. So, that is going to be not possible, because with the probability 1 it moved to the state 0, therefore, this is going to be 0. And if you find out f 1 1 of all the subsequent steps also, that is also going to be 0, because if the system start from the state 1, in the next step itself it goes to the state 0 with the probability 1 and it is not coming back. Therefore, now we try to find out what is a capital F 1 1, that is nothing but the summation of all the Fi's, summation of all the Fi's, and that is going to be 0. If you recall the way we classify the state is going to be a recurrent or transient, we said f I a is going to be 1 or f I a is going to be less than 1. So, that less than 1 includes f I a is equal to 0. So, basically our interest is to classify whether with the proper distribution the system is coming back to the same state with the probability 1, that is f I a is equal to 1, and all other things we say that is a transient state, it includes f I a equal to 0. So, here with the probability 0, the system is not coming back to the state 1 if the system start from the state 1. This is always a conditional probability, and this conditional probability f 1 1 is equal to 0 implies the state 1 is going to be a transient state. So, whenever for any state I, f I a is equal to 1, that concludes the state is going to be a recurrent state, and whenever the f I a is lies between including 0 excluding 1, that is less than 1, then that state is going to be called it as a transient state. Since since you have only two states, that is the state space is 0 and 1, and you will end up having a one observing state and one transient state. Therefore, the state space is partitioned into one closed communicating class which has only one element, and the transient state is 1. Therefore, I can say the state space S is a partition into closed communicating class C1, which consists of only one element, and the collection of all the transient states, that is only one element. So, this is a notation for capital T collecting all the transient states in the state space in the DTMC, and C1 is the first closed communicating class and which has only one element, If any closed communicating class has only one element, then it is going to be called it as observing state. Therefore, 0 is the observing state and 1 is the transient state. Since you have a C1 union T becomes a state space S, therefore, this Markov chain is not a irreducible Markov chain. Therefore, this is called a reducible Markov chain. This Markov, whereas the previous example is a irreducible Markov chain. There we have two elements and both the elements form only one close communicating class, whereas here you have one close communicating class with one element and the transient state is 1. Therefore, it is going to be a reducible Markov chain. There can be more than one transient state. Now, I am moving into the third example, so that I am explaining some more concepts through the examples. Example 3. Here I will go for 4 states which consist of states 0, 1, 2 and 3. It is easy to explain through the state transition diagram than the one step transition probability matrix. So, I am just drawing the state transition diagram for this DTMC. So, 0 to 0 one step, that probability is 1/3 and 0 to 1 is a 2/3. Therefore, rho sum is taken care, that probability summation of probability is 1. Now, I am going for the state 1. State 1 to 0, that probability is 1, therefore, that row is taken care. Now, I am moving into the state 2. State 2, the self loop has the probability of, and going from the state 2 to 0, that probability is off. Therefore, this row is also taken care. Now, I am moving into the state 3. State 3, it has the self loop with the probability of, and it has the moving from the state 3 to 2, that probability is off. My interest is to classify the states for this Markov chain. Markov chain has 4 states 0, 1, 2 and 3, that is a state space capital S. Now, we will start with the state 0. So, you find out what is F00 of 1. In one step, as a first visit, the system has to come back to the same state 0. So, that probability is 1/3. You find out F00 of 2. F00 of 2, exactly 2 steps, as a first visit you have to come back to the state 0. That means, you can go to the state 1 by starting from the state 0 and come back to the state 0 in the next step. Therefore, it is a 2/3 into 1, therefore, it is going to be 2/3. Then you go for what is the possibility, I will take 3 steps, exactly 3 steps coming to the state 0. As a first visit it is not possible, whereas the P00 of 3 is possible. F00 of 3 is not possible, because in 3 steps you cannot make a first visit. Therefore, that is going to be 0, not only F00 of 3, and for all other things also it is going to be 0. F00 of n equal to 0 for n is greater than or equal to 3. So, now I can find out what is capital F00. If I find out capital F00, I have to add all the values. So, it is 1/3 plus 2/3 plus all the further terms are 0, therefore, it is going to be 1. Since F00 is equal to 1, you can conclude the state space 0 is the state 0 is going to be the recurrent state. The similar exercise you can do it for the state 1. the same way you can conclude f11 is also going to be 1. The other way, since the state 1 is communicating with the state 0, since the state 1 is communicating with the state 0, therefore, this is also going to be of the same type. Therefore, the state 1 is also going to be the recurrent state. Now, we can go to the state 2. So, the state zero comma 1, that is going to be the recurrent state. Now, I will move it to the state 2. So, whereas the state 2, if you find out f 0, f 2, 2 of 1 in one step coming back to the same state, that is going to be of f 2, 2 of 2 steps, exactly 2 steps, that is not possible, that is going to be 0, and so on. Not only 2, and all the further steps also going to be 0, because with the probability of it takes only one step come back, and all the further steps it takes with the probability of it is not coming back at all. Therefore, this is going to be for greater than or equal to 2, it is going to be 0. Therefore, if you compute f 22, capital F 22, then that is going to be off plus 0 and so on. Therefore, you will end up off which is less than 1. Therefore, you can conclude the state 2 is going to be transient state. Not only the state 2, if you do the similar exercise for the state 3, the same thing, you may land up f 33 is also going to be less than 1, whatever be the number, you can conclude the state 3, that is also going to be the transient state. You can find out the periodicity for the recurrent state only, not for the transient state. Therefore, now we can try to find out what is the periodicity for the state 0 and 1. Before that, we will try to find out what is the type of recurrent state, whether it is going to be a positive recurrent or null recurrent. If you find out mu 0 0, mu 0 0, that is nothing but 1 times 1/3, 2 times 2/3, 3 times 0, 4 times 0 and so on. So, if you sum it up everything, you may land up 1 times 1/3 plus 2 times 2/3, that is going to be 1/3 plus 2 times 2/3. So, that is going to be 3, 1 plus 4, that is 5. So, which is a finite quantity, you can conclude the state 0 is going to be a positive recurrent. Similarly, if you calculate f mu 1 also, you may land up with the finite quantity. So, you can conclude both the states are going to be a positive recurrent states. Here the state space is classified into 2 positive recurrent state and 2 transient state. Therefore, this Markov chain is going to be a reducible Markov chain, in short form MC. It is a reducible Markov chain because the whole state space capital S is partitioned into one closed communicating class which consists of the state 0 and 1 and the transient states 2 and 3. Therefore, this is going to be a reducible Markov chain. You can find out the periodicity of these 2 recurrent state also. So, if you find out D0, that is going to be greatest common divisor of what are all the steps in which the system will be come back if the system start from the state 0. So, either it can come back with the 1 step or either it can come back with the 2 steps or it can make a 1 loop here, then 1 loop, then here. Therefore, it can come back from the 3 steps and 4 steps and so on. It need not be the first visit. Therefore, the GCD of 1 step or 2 steps and 3 steps and so on, therefore, this is going to be 1. That means it is a aperiodic state. Therefore, whatever we have done it for the state 0, you can do it for the state 1 also. So, that is also going to be 1. The period is going to be 1. Therefore, both the states 0 and 1 are the positive recurrent and aperiodic states, and other two are going to be the transient states. Since this state 0 and 1 are going to be positive recurrent as well as aperiodic, and these two states are ergodic states also. Later we are going to explain ergodicity, the property. For that property you need to understand what is ergodic state. So, whenever the Markov chain has a few states going to be a positive recurrent and aperiodic, then those states are going to be called it as a ergodic states. So, later I am going to give the definition of ergodicity and so on. Now, we are moving into the fourth example. That has now we are moving into the fourth example. This has the infinite number of states. Suppose the state space, let me draw the state transition diagram, state 0, 1, 2 and so on. The left hand side it has the states -1, -2 and so on. So, the state space of this Markov chain has a countably infinite number of elements with the state 0 plus or minus 1 plus or minus 2 and so on. Let me give the transition rates, transition probabilities. So, the system is moving from state 0 to 1 with the probability p, and the system is moving from the state 0 to -1 with the probability 1 minus p. Therefore, if you see the state transition diagram, state one step transition probability matrix, the row sum is going to be 1. So, you keep p is lies between, p can lies between 0 to 1. Similarly, you go for the all other states. The system is moving from the state to the forward one state, that is with the probability p, backward state with the probability 1 minus p. With the forward is p and coming back to the one step less, one state less, that is 1 minus p. So, this is the way it goes for all the states. 1 minus p and this is 1 p, and you have a countably infinite number of states. Fine. Now, let me go for the case 1 in which the p is going to be 0. Suppose p takes the value 0, what happens, or how to classify the states when p is equal to 0 in this time homogeneous discrete time Markov chain. When p is equal to 0, there is no forward arc. When p is equal to 0 implies the system is always go to the one state, one step less, one state less with the probability 1, because p equal to 0. Therefore, you should be able to visualize what is the state transition diagram corresponding to p is equal to 0. There is no forward arc arrows. That means, whenever the system start from some state, it will keep on going to the one state less in every step, and you can visualize for a longer run where the system will be, whether it will be in the positive side or in the negative side. You can visualize whenever the system start from any finite state over the period, it may be in some state with some positive probability for the finite number of steps. for a infinite number of steps or for a longer run, the system will be in the negative side for a longer run. So, that is a limiting distribution, but here we are discussing the classification of the states. Therefore, with the probability 0, it will not be back at all. If the system starts from any state, it will not be back to the same state with the probability 0. Therefore, all the states are going to be the transient states. If you calculate f for you take any finite state 1 or something, then f 1 1 of 1, f 1 1 of 2 and so on, if you calculate, then you may land up f 1 1 capital 1, that is going to be always less than 1. Therefore, if you start with the one state, you can conclude it is a transient state, and all other states also are of the same way. Therefore, all the states are going to be same. Suppose we discuss the case 2 with the p equal to 1, what happens? If p equal to 1, then you have all the forward arcs, not the backward arcs. That means whenever the system starts from any state, then the system will go to the forward all the states in subsequent steps with the probability 1. In a longer run, the system will be in the positive side, positive infinite side in a longer run. Therefore, with the probability 0, it will be in any one of the finite states in a longer run, whereas for the any finite steps, the system will be in some of the states and it will be keep moving forward state over the number of steps. Therefore, here also you land up all the states are going to be transient states. Both the two cases, the situation for the limiting distribution may change. One is in the left side, the other one is in the right side, whereas all the states are going to be the transient states. But our interest is for the p is lies between, that is our third case. Our interest is p lies between 0 to 1, open interval. That means if you see the previous state transition diagram, you have both the forward arcs as well as the backward arcs, because the probability p is lies between open interval 0 to 1. Therefore, the 1 minus p is also lies between 0 to 1 in the open interval. Therefore, whenever the system starts from any state, it will come back to the same state with the even number of steps. Suppose you visualize with the state 1, it can come back to the same state 1 not in the odd number of steps, but in the even number of steps. Suppose if the system moves to the state 0 in the first step, and in the second step it can come back to the state 1. Similarly, suppose the system would have moved from 1 to 2, then in the second step it would have come to the state 1. Therefore, it is a 2 steps it can come back either via going to the state 0 or going to the state 2. Suppose you go for think of 4 steps it coming back to the same state, that is possible, need not be the first visit, means it can make a 2 times loop in the left side, or it can make a 2 times a loop in the right hand side, or it can make a 1 step forward and 1 more step forward, then it can come back. Therefore, all the possible steps, if you include all the possible steps, you will come to the conclusion it will take a even number of steps to come back to the same state. So, if you do the simple exercise what we have done it in the earlier case, you can come to the conclusion 0 plus or minus 1 plus or minus 2 and so on, all the states are going to be a recurrent state. Without fixing the value p, you can conclude f I I, capital F I I is going to be 1 for all the states. Therefore, now we come to the conclusion all the states are going to be the recurrent state. If you try to find out the periodicity for any state, the way I discussed, the greatest common divisor of the greatest common divisor of n such that the Pii of n, which is going to be greater than 0, and this is possible for all the even number of steps. Therefore, the system will be come back to the same state 2 steps, 4 steps, 6 steps and so on. Therefore, the GCD is going to be 2 for this particular Markov chain. So, the period is going to be 2 and the recurrent state. Now, our interest is whether these states are going to be a positive recurrent or null recurrent. But for that you need what is the value of p, because without p, without the value of p, you cannot come to the conclusion the mu suffix I that is going to be n times Fii of n. You need the value, but some example it is not, it is possible, but still by supplying the value of p or what is the range in which you can conclude whether this is going to be a finite quantity or going to be infinite quantity. Based on the range of p, you can conclude these recurrent states are going to be a positive recurrent or null recurrent. Since the state space is going to be 0 plus or minus 1 plus or minus 2 and so on, and all the states are going to be a recurrent states, it will form a one closed communicating class. Both are all the states are communicating with each other. Therefore, you will end up having a only one closed communicating class which is same as the state space. Therefore, this is going to be a irreducible Markov chain. These states may be a positive recurrent or null recurrent based on the range of p, but here we are just concluding this is going to be a irreducible Markov chain with all the states are going to be a recurrent with the period 2. So, since the period is 2, it will not be a ergodic states also. If you want a ergodic state, you need a positive recurrent as well as the aperiodic. Since the period is 2, you can conclude this is not going to be the ergodic state. I am going to give the next example, that is example 5, which has the finite states 0, 1, 2, 3, 4 and the one step transition probabilities, that is 1/3, 2/3, and for the state 1 with the probability 1 it moves to the state 2, and for the state 2 with the probability 1 it moves to the state 0. For the state 3 with the probability of it goes to the state 4, with the probability of it goes to the state 1. For the state 4 it is with the probability of it goes to the state 3, with the probability of it goes to the state 2. The way I have drawn the state transition diagram, by taking care the row sum is going to be 1. So, you can equivalently have a one step transition probability matrix also. So, here I have only the state transition diagram for this DTMC. From this diagram, either by calculating Fii and capital Fi, you can conclude it is going to be a recurrent state or transient state. Then you can conclude whether it is going to be a positive recurrent or null recurrent. But whenever the Markov chain is going to be finite, without doing the calculation, from the diagram you can conclude these states are going to be a positive recurrent and these states are going to be a transient states. So, that I am going to do, but the same exercise you can do it and get the result also. The way the arcs are here, if you see the state 3 and 4 states 3 and 4, it has the only outgoing arc to the states 1 and 2, whereas 0, 1 and 2 has the loop form, and the state 0 has the self loop with the probability 1/3. Sometimes if the outgoing arcs, the probabilities are not going to be 1, that summation, that means you can make out the self loop as the probability 1 minus of all the outgoing arcs, but that is a default scenario. But always we should draw the correct state transition diagram. If it has some positive probability with the self loop, we should always draw the self loop with the positive probability. That is the correct way of drawing the state transition diagram. So, now you can make out the state 0, 1 and 2 are forming some sort of loop. That means, if the system start from the state 0 or 1 or 2, it will be only within these 3 states over the number of steps. Even for a longer run, the system will be any one of these 3 states only. So, these 3 states will be communicating each other, not communicating with the states 3 and 4, whereas there is accessible from the state 3 to 1, but there is no accessible from 1 to 3. Therefore, 1 and 3 are not communicating states. Similarly, 2 and 4 are not communicating states, because one side accessible is here, not the other side accessible. Therefore, you can make a set 0, 1 and 2, you cannot include any more states to form a set, and this set satisfying the property closed as well as communicating. So, this set is called a closed communicating class, and all these 3 states are communicating each other. And if you find out a f capital F 0 0, capital F 1 1, capital F 2 2, so on, you come to the conclusion that value is going to be 1, and all these 3 states are going to be a positive recurrent states. Whereas the states 3 and 4, if the system start from the state 3 or 4, it has the loop structure with the probability of, but with the probability of, it can go to the state 2 or it can go to the state 1 via state 3 or via state 4 accordingly. Then land up, the system is not coming back to the state 3 or 4. Once it is going away from the state 3 and 4, starting from these states, it is not coming back. Therefore, these states 3 and 4 will form a transient states. Even though the state 3 and 4 are communicating each other, these states will form a transient state, because f 3 3 and f 4 4, it is going to be less than 1. And if you try to find out the periodicity of this state, you can find out the periodicity of any one state, then that is going to be the period for all other states in the same class. Therefore, if you find out the periodicity of the state 0, that is d 0, that is the greatest common divisor of what are all the steps, the system will be come back to the same state. So, either it can take 1 step or 1, 2, 3, 4, or it can take only 3 steps, not making a self loop, 1, 2 and 3. So, it can make a 1 or 3 steps or 4 steps or 5 steps. 5 steps means it makes a 2 steps self loop, then third step going from 0 to 1 and 1 to 2, then 2 to 0. Therefore, it is a 5 steps and so on. Therefore, the greatest common divisor is going to be 1. So, since the period for the state 0 is going to be 1, this is going to be a periodic state, and all the states are going to be a periodic states. Since these states are the positive recurrent aperiodic, these states are also going to be called it as a ergodic states. These states are going to be ergodic states. Since the state space S has the union of the close communicating class and these transient states, therefore, this is going to be a reducible Markov chain. So, in this example we come to the conclusion we have 5 states and this is going to be the reducible Markov chain because of the close communicating class is consists of elements 0, 1 and 2 and the transient states are 3 and 4. Moving to the next example, example 6. In this example, I have a six states and the one step transition probability values are 1/4 and 3/4 it goes to the state 4 and for the state 1 it is off and this is also off. For the state 2 with the probability 3/4 it goes to the state 5 and with the probability 1/4 it goes to the state 4. Whereas, for the state 3 there is nothing. For the state 4 with the probability 1/3 it goes to the state 2 and 2/3 it goes to the state 3. Since there is no outgoing arc in the state of 5 and 3, you can make out the self loop has the probability 1 or you can draw also with the probability 1. So, now we can go for classifying these states. Because of the self loop with the probability 1 for the state 3 and 5, you can directly make out the state 3 is going to be observing state and this is going to form a one class C1. This close communicating class has only one element which is state 3. Similarly, I can go for the second class which has the only one element that is state 5, that is also observing state, that is also observing state. Now, I can go for classifying the state 0, 1, 2 and 4 because it is a finite state discrete time Markov chain. If the system start from the state 3 or 5, it will be in the state 3 or 5 forever because both are observing state. If the system start from other than the state 3 or 5, ultimately it comes to the state 3 or 5 via this 2 to 5 or 4 to 3, then it will not be back. Therefore, all these states 0, 1, 2 and 4 will form a transient state. So, this is a collection capital T, that is 0, 1, 2 and 4 are going to be form a transient states. I have not computed what is F00 or F11, F22, F44. Since it is a finite Markov chain and these two states are going to be observing state, whenever the system start from the state 0 or 1 or 2 or 4, either it will make a loop or ultimately land up to the state 5 or 3 with this aux. Therefore, these 4 states are going to be a transient states and this will make a reducible Markov chain. Suppose the system start from 0 or 1 with the arc 1 to 2 or 3 to 4, either the system can go to the state 2 or state 4. If the system start from the state 0 or 1, Either the system can go to the state 2 via 1 2 or state 4 via 0 4. Then after that it will be keep roaming here 2 and 4, but with the positive probability 3/4 and 2/3 it can go to the state 5 or state 3. Therefore, these states are going to be observing state. Therefore, ultimately the system will land up the state 3 or 5. Therefore, these states are, therefore, this is a one type of reducible Markov chain in which you have a transient states and few observing states. Now, I am moving into next example. This is another type of reducible Markov chain, that is example 7, which has the finite states n plus 1 states, and the transitions are like this. With the probability 1 minus p, the system goes to the state 1 to 0. With the probability p, it can go to the state 1 to 2, and this probability is 1 minus p and so on. So, all the forward arcs are p and the backward arcs are 1 minus p, whereas here this is p, there is no forward arc, therefore, the state 0 and n is going to be observing states. So, here the p can lies between, later I am going to explain this same DTMC for the gambler's ruin chain problem, and here we have a n plus 1 states with the state 0 and 1 are going to be observing states. We usually write observing states individually because each one will form a close communicating class, but here I have written both the states are observing states, and all other states 1 to 2 till n minus 1, those will form a transient states, because if the system starts from these states 1 to n minus 1, it can keep move between these states over the number of steps, but with the positive probability of 1 minus p, it can go to the state 0. With the positive probability of p, it can go to the state n in this group of transient states. So, once the system come to the state 0 or n, then it will be forever. It is basically therefore, we can come to the conclusion this is going to be the reducible Markov chain of the type transient states and the few observing states. So, with this let me stop the examples of classification of states. That means, I have given the 7 different examples in which it has the finite Markov chain as well as the infinite Markov chain, and a few Markov chains are the reducible, few are irreducible. In reducible Markov chain, we have made 2-3 types of reducible Markov chain, that also I have explained. In the next class, we will discuss the limiting distribution and the stationary distribution. Thanks.